Lecture 20, more about input and output devices. So in the previous topic, we just discussed the idea trying to do a read, and we said, well, there's some work that's done on the part of the device driver to translate our request into an actual hardware operation. And so if I want to do something like read a file called example.txt, right, the file system, which we will come to shortly, has to associate this file with a location of some sort on disk. And then to read the file, read commands will be issued to get those blocks into memory, and then I can edit it with my text editor, and that's enough for it to be useful, right? Now, the I/O request lifecycle is actually sort of fairly long, right? And at the top row there, we're inside the user process. And so the user process wants to request I/O, so that's when we have a read system call or something to that effect. And when the read call takes place, as we've discussed on more than one occasion, right, we end up with a trap to the system call, which activates the operating system. Now, sometimes it is entirely possible that whatever we've asked for is already available for whatever reason. And if that's the case, then there isn't really much need to go to disk or sort of do anything, any other hardware operation, so that's okay. And if that's the case, then we will just satisfy that request with the data that we already have. We'll return the result, right? How does this happen? I mean, there's several different ways in which it can happen. The important thing effectively is just that, like, okay, the data that we asked for was already in memory. Maybe another process has already asked to read that, and like, hey, we have the answer at hand. Maybe it's a shared segment, so yeah, we know that the data is already there. In which case, we can take this little shortcut across the diagram to the box in the right-hand column where we transfer the data to the process and return completion or the error code, right? Because when you read, you say, please, I would like to read this many bytes into this destination, and we will then move the data into that destination before we consider the operation complete. It's also possible, you'll notice that box mentions an error code. It's also entirely possible that we'll identify at this stage that the request is impossible, in which case we can just return the error code right away and the hardware never gets involved. Okay, but let's imagine actually that we don't have to do that and the I/O operation will proceed as normal. So if that's the case, then the problem, the request is handed off to the kernel's I/O subsystem, and in the I/O subsystem, it will send the device driver the request that we're looking for, and at that point, if it was requested as a blocking operation and read is a blocking operation, we will block the calling process and cannot continue until the data there is ready. And then it's the job of the device driver, as we've talked about, to process the request, issue the commands to the controller, configure the controller to block until interrupted. We are assuming some sort of interrupt-based I/O in this diagram, but all that seems fairly doable. And then there's like a box that's missing there where it says device controller commands, magic of hardware. Things happen, and somehow Palpatine returned. Somehow the data gets transmitted to the I/O device, or the request is sent to the I/O device, and that's enough for us to proceed. And at this point, we're just waiting for the interrupt, or as we discussed previously, if there's polling, we might actually poll until the data is available. I mean, we don't like it, but it can happen, so yeah, we acknowledge that it could be like that. And when the I/O is completed, an interrupt is generated. And the device controller is going to send an interrupt, if it is in fact an interrupt-based kind of device. And that's great because that's what we need such that we are able to continue. And the interrupt handler can wake up and store the data in a device driver buffer. If this was input, and for the sake of our example, it's a read, so yes, it is. And that just sort of packs it in somewhere that the kernel can access it when the kernel is ready to deal with it. And we also need to notify the device driver that the operation that was requested has completed. And the device driver will update the state of the I/O subsystem, i.e. the device is no longer busy or has moved on to the next request. And that is fairly straightforward. And then we can return the data to the kernel I/O subsystem, and then we're finally in sort of the last stages of the process where we transfer the data to the requester. And however we got here, even if we took the shortcut, there is return from the system call such that the user process continues executing and the data is available. Okay, so I mean, there's a few steps here. We haven't really talked about how long these different steps take because it is, of course, highly variable on the nature of the I/O device in question. Right? Reading from a hard drive is fairly slow, and so requesting some data from a physical disk drive, it's not forever, but it's not instant either. But if it's over the network, I mean, it might be faster than going to disk, but it might be slower. Depends. Is it a local network, or are we requesting something that's on a server in New Zealand? It's going to be highly variable. And some operations take longer than others, right? Something that is fire and forget, we don't have to wait for the results to be returned. We could just say, yep, when we've successfully transmitted the request to the hardware device, that's it, we're finished. We just return some message that says, yes, we have successfully transmitted it. Moving on. All right. Regardless of whether a device is block or character oriented, the operating system can improve its performance through the use of buffering. And a buffer is nothing more than just an area of memory that stores data being transferred, whether it's from memory to device, device to memory, or between two devices. And you may have experienced using a buffer speeding things up. One of the examples I can think of is in Java, you want to read a file. If you use a buffered reader, it is significantly faster than just using a regular I/O reader. Why is that the case? Well, the buffered reader is more efficient, and we can talk about why this is the case in a bit. But yeah, it's just like a temporary area where sort of memory is used for storing some data. And you might be familiar with buffering from something like watching an online video, right? When you watch an online video, sort of whatever video it is going to be potentially delivered to your computer faster or slower than you're watching it, right? If each piece of the video is delivered just in time, right, even a small slowdown or hiccup will actually cause problems. Right, you will get the video pauses, or it stutters, or maybe degraded in quality temporarily until the next chunk arrives, and probably you didn't want that, right? All things being equal, you would prefer a nice, smooth video watching experience, so that it doesn't constantly get interrupted, and it's very frustrating when it stutters a lot. Right, and so to give a smoother experience to the viewer, the video player most likely will get and store the next few chunks of the video a little bit in advance. So if there is some temporary delay in getting a chunk, then playback is not interrupted. And this video playing example is fairly simple, but it covers everything that's truly important about the use of buffers. We need a place to store the data temporarily, because this decouples producing, which is sending it from the server, and consuming, playing the video. It requires decisions about how big the buffer should be. How big should it be? I mean, there's a temptation to say that bigger is always better, but I don't think that's entirely true. Right? If the video player wants to have n chunks before starting the video for a larger value of n, it delays the start of playing the video. And if n is very large, users become frustrated because they came to this page to watch this video and it's taking a long time for it to launch, and why Why is this the case? Why can't the video start a little bit sooner? Another reason is we might do some unnecessary work. If viewer starts the video and then decides to skip forward by 30% of the video because the introduction is boring and nobody wants to watch that ad for the stupid mobile game, the player will have downloaded some chunks and potentially even decoded them that were not needed. If you have a super fast internet connection, maybe you don't care because the costs are very low. But if you're doing this with a limited connection, poor service, metered connection, what have you, that actually starts to feel kind of painful. And so if you want to have a good user experience, you are balancing effectively the size of the buffer with the user's needs. Because, too big of a buffer, we're wasting too much time and too much effort. Too small of a buffer, and we have this stuttering playback experience. And, I mean, realistically, there's no reason why you have to choose one size for all users. You can test the speed of the internet connection or the latency of the internet connection for the person who's watching the video, and you can set the buffer appropriately. But it is a consideration, and it is at least a little bit complicated, more so than we might imagine. So here's a calculation that's a little bit crude, but it shows you, at least in a small way, performance impact of using a buffer. If we say that capital T is the time required to input one block and capital C is the computation time between input requests, with no buffer, the execution time to complete a block is T plus C. Whereas with a buffer, it is max between C and T plus M, where M is the time to move data from a system buffer to process memory. Okay, right? We are taking the chunks and we are putting them into memory somewhere, and we can sort of return to them later if we wish. It is nice, it is convenient, and it is a little bit better than just trying to take them one at a time. It's better to have something at the ready at all times. This is going to branch into sort of more advanced stuff than we are really intending to talk about. But if you've ever wondered, why is it if I go to, I don't know, the doctor's office or something, even though my appointment is at 10:30, the doctor doesn't actually come see me for a while, even after I get there. Some of that is just there's delays because the doctor had a 10-minute appointment with somebody, and in minute 9 they said, oh, actually I've been having this chest pain. And the doctor was like, you probably could have opened with that. That might have been more important than your toenail. But there's that kind of thing. But the other reason is trying to keep it so the doctor is busy at all times, right? The doctor's time is valuable and is a limited resource, and effectively you're being asked to wait, in a little buffer, so that there's never a situation where the patient is a little bit late, and the doctor has no patient to see right now. Even though I'm sure the doctor would love to have a coffee or a tea break or something, that's just kind of not how it works. So that's part of the reason why. And this sort of buffering is relevant even when we're not talking about computer type stuff. Okay, now a buffer is normally created with a bounded capacity. The buffer can hold some number of bytes X, and once that buffer is full, nothing else can fit in there right now, and so we have to make some choices about what is supposed to happen. One option, of course, is to just overwrite stuff. Another option is to block new data, block the processes or threads that want to add new data until space becomes available. And we've talked about a number of these sorts of problems in the past. We've talked about the producer-consumer problem, and bounded buffers and that sort of thing. Sometimes book talks about buffers of unbounded capacity. I don't really favor this because infinite capacity isn't real. There's always a limit, and an unbounded capacity channel or whatever might be able to hold arbitrarily many items up to the memory limit of your system. And that might be a huge, absurdly huge amount, more than you ever need to worry about, so there's no sense in worrying about it. But I don't think it's fair to call it truly unbounded, because there is eventually some sort of limit for how much you could possibly put in there. And so I much prefer the idea that we consider that things will run out and we act accordingly. Right? The memory space of the system will run out. It's even if it's after 30 terabytes, that seems like a very large amount of data, and at least at the time of recording, it certainly is. And I imagine one day if somebody watches these in 100 years and you'd be like 30 terabytes, like, my watch has 300 terabytes. But that's fine. That's how technology works. But at least right now, that's a lot of time and a lot of space. And yeah, we would have the same problem even when we reach this limit, no matter how absurd it is, that we have to make a decision about what to do when the buffer is full. So I would prefer we deal with that sooner rather than later, by effectively not pretending that it won't happen. It's convenient to pretend that it won't happen. That I certainly grant, but I don't think that's realistic. So, okay, suppose we would like to implement a buffer. And implementing a buffer is relatively straightforward from the point of view of the operating system, because it really only requires two operations. And add something to the buffer and remove something from the buffer. Does that sound familiar? I mean, I sincerely hope so. And if you didn't enjoy ECE 252, this slide might make you feel a little uncomfortable. But yeah, if you remember the producer-consumer problem, we are effectively talking about that same thing. I mean, the other name for the producer-consumer problem is this bounded buffer problem. And so, yeah, does that seem familiar? Yeah, here's the pseudocode version. Are you tired of seeing it yet? Okay. So the important thing to note is that the use of the mutex and the semaphore will block and unblock threads is necessary when the buffer is full, when it's being modified, and also when it is empty. So you can also choose if you want to use the simpler version where there's no mutex, when you have only one producer and only one consumer. And we were able to show that using these things correctly produces the right results even in the absence of a mutex when there's just one producer and one consumer. So what does a buffer look like from the point of view of the operating system? Well, it looks just like this. Okay, now, not too long ago, we talked about sort of speed mismatch between devices and suggested maybe that typing text should go into a buffer. Because really, I mean, the user writes very slowly as compared to the computer, and it feels a little bit weird to just hold up the normal execution of the program, while the user types in one character at a time. Even if you're a fast typer, as far as the computer is concerned, you are handing in characters here one at a time. So now what, right? When the buffer is full, write it out to disk. But what do we do then, right? Because during the write is not instantaneous, and so we have to do something with the incoming data while the buffer write is on the way out. So what do we do? Okay, well, the slide title gives it away. And the typical solution for this is called double buffering, which is to say there are two buffers. And so while buffer 1 is being emptied, new incoming keystrokes go into buffer 2. And this helps to overcome sort of the speed mismatch between the two operations. Sending in data is slow, but writing it out takes non-trivial time as well. And as long as we do this correctly, then whenever data comes in, it will go to whichever buffer is currently being filled, and the other buffer can be emptied in that time period without too much concern. The obvious extension of this is more buffers, so if you need more than two, then we talk about circular buffering. Each individual buffer is being sort of one of many in the big ring of circular buffers, and that is fine, right? That's not too exciting, and I think we can work out just based on what we've seen so far how it's supposed to work. So I don't think we need to spend a lot of time belaboring that particular point. Okay, but here's the thing: buffering is great, but it's not magic, and it cannot possibly solve all problems. And what I mean by this is if the rate at which the buffer or buffers is or are being filled consistently exceeds the rate at which they're being empty, at some point all the buffers will be full. Right? There's never going to be unlimited capacity. I mean, we talked about that just a minute ago. And try as we might, we can maybe ignore it a little bit, but realistically, no, we can't. And so buffering is good for smoothing out the peaks and valleys in the data transmission, but they aren't a complete solution because there is indeed always the possibility that the buffer is just full. Right? Or empty if it goes the other way. And that's a distinct possibility as well. And again, there isn't really anything wrong with that. It's just that you have to plan accordingly. Right? Tempting as it is to say that will never happen, or it's rare enough so that it's no issue, I think we know that's not true. And maybe it doesn't happen in testing, but this sort of thing certainly could happen in live system. So when the buffer is full, the buffers can hold no more, so producers need to get blocked until such time as there is some more capacity. And if the buffers are completely empty, if they're being emptied much faster than they can be filled up, then again there will be a time when the buffers are completely empty. And if that's the case, then we need to block the consumers until there is at some point some new thing to consume. So yeah, it's buffering is great and highly recommended in many circumstances, but ultimately it may not be the perfect solution because it may mean you need to increase the capacity for the producers if you are consistently sort of running out of things to do, or increase the capacity for consumers if you are constantly having the buffers full. Okay, so that ends our little side component about buffering. So let's also talk about I/O scheduling and performance. And when we talk about I/O scheduling in this context, right, what I mean is that there are multiple I/O operations that could be in progress at any given time, right? However many requests have been created and however many requests the OS is currently working on is variable with time and not really in the control of the operating system because user processes can request things whenever they want. Whether we like that or not, I don't know. But like we talked about for, say, a semaphore, the operating system needs to keep track of device status and have a queue for each device so that we understand where the thread is blocked. If the thread is waiting for something, you're waiting your turn to send data over the network or something like that, well, we need to have a way of keeping track of the fact that this process is blocked, trying to access the network. Just as we've discussed for the semaphore. So that makes sense. But how do we manage the queue? Well, I would say it looks significantly like many of the other things that we've discussed already. When a thread wants to use the device, we can check the device status. If it's available, mark the device as busy, submit the request immediately. If a thread shows up and wants to use the device that's already in use, block it and add it to the queue. When the operation is complete, unblock a thread that's waiting and let it continue. If there's no further requests, mark the device as idle, not in use. Otherwise, keep the status as busy and begin the next request. So in that sense, it looks kind of like a mutex, but all right, that shouldn't be too surprising given what we know. And that is at least a little bit probably how we think about this sort of management of such a structure. Okay, now the scheme that I just described is first come, first served. And if that's the case, right, well, it's maybe adequate. It's fair, but it's not necessarily optimal. We've discussed in scheduling the idea of how do you give a process priority, and sometimes priority is based around the idea of just choosing how to schedule it for CPU time, but there's no reason why it couldn't also apply to, well, we use it for choosing how to schedule I/O. So maybe a higher priority process's I/O request gets to go first, and a lower priority process's I/O request has to wait. right? That's plausible. There's usually some limits on these things to prevent starvation, but logically speaking, I can't see why this wouldn't work. Right? Fair, but maybe not optimal. And one of the reasons why it might not be optimal is, what if devices have non-uniform access times? We usually talk about I/O requests sort of as if every operation takes the same amount of time. And for some kinds of devices, that's true. If we're reading a file off a USB flash drive, it doesn't really matter where on the drive that data is physically located, because read and write times are the same no matter what. But that's not true for every kind of device, and we'll examine in some detail later on the application of this to hard drives and why it matters in terms of scheduling hard drives. But you could easily imagine also, say, for network, right? That a network request takes a variable amount of time depending on what is the remote system. Is it another server inside our same network because we're validating the login and password that have been provided? That might be fairly quick. Or are we trying to download some data from across the internet, and the server is located in Singapore? That's going to be slower as compared to the local network access. So it's fair to say that we have some non-uniform access times, because the amount of time that it takes to get an answer does vary. It's not bad, but it is a consideration that maybe you would try to choose the things that will be finished sooner because that helps them get out of the way, or maybe you choose the ones that will take longer because it means they get started and don't get delayed any more than is actually necessary. There's a lot of considerations that go into it, right? And in a very simple analogy, in terms of like efficiency for this non-uniform memory access kind of time, the analogy that I like to use is like if you need to go to the grocery store, the dry cleaners, and the bank, and let's imagine the bank is 1 kilometer to the west of your current location, the grocery store 3 kilometers west, and the dry cleaners in the same plaza as the grocery store. Okay, so it would be fine to go to the bank, then the dry cleaners, then the grocery store, but we don't want to go to the dry cleaners, then the bank, then the grocery store, because there would be some unnecessary back and forth, right? In the end, all the things need to get done, and that is more important than doing them in the absolute optimal way. However, if we can, we would like to avoid that sort of unnecessary back and forth, just because, like, what's the point, right? We're wasting time, we're wasting, if we're walking effort, if we're driving fuel, and why do that? Why would we not prefer to accomplish things in the most efficient way that we can? And that would usually be preferable. And the same thing applies to certain I/O devices, that it would actually be better to accomplish them as efficiently as possible. To make that happen, the operating system has to have sort of some idea of what the I/O requests are, and so it knows what requests are outstanding, and then it can try to reorder them in a way that is more efficient than they would be if it was just first come, first serve. Such a process has to have a limit. We can't delay doing a request forever because it would be too inconvenient. There are some chores that you just can't skip. Do I want to pay my taxes? No. Can I procrastinate that forever? Also no. It might also take priority into account if it's going to reorganize the order in which these I/O requests take place. Now, in the literature, sometimes they talk about there being an I/O queue, but I'm hesitant to use that word because queue usually implies like first in, first out kind of behavior, and we're saying we explicitly want to break that expectation. So I choose not to call it that, but certainly we have an I/O request structure. Okay, next question. Next question is based around the idea of, can a system be too responsive? Is there too much of a good thing? And we've covered the idea that interrupts are already more efficient than polling. Great. We like interrupts, and polling is kind of painful. But network traffic may potentially cause a lot of interrupts and a very high rate of context switches. And here's what I mean. if we're downloading a file, there's a video and you're downloading the video so you can watch it. The number of context switches to accomplish this goal is not a tiny number necessarily, but it seems manageable. Because every time a chunk of the video is downloaded, then it gets added to the little player in your browser window, and before you know it, you have enough chunks that you can get started, and congratulations, you're watching video number 20 of me talking to you about real-time operating system. Now, that kind of thing is okay, but eventually, of course, all the file is downloaded and we're finished and there's kind of nothing else to do. But that's not really the model for every kind of network operation. And let's imagine that I'm in a lecture and I want to demonstrate some code executing. And you probably saw me do this either in ECE 252 or watching a video of me tinkering with some things in the course. And here's what happens, right? So I'm logged into ECE Ubuntu so I can run the code, and I type in my editor. So I press a key locally. Let's say that I've chosen the letter Z as the key that I'm pressing. What happens here? So I'm editing a C file, right? And you'll notice like there's 6 elements that appear in the list. So there's a keyboard interrupt locally, right? I've pressed the key on the physical keyboard that is in front of my hands, and that generated an interrupt for the operating system on my laptop. The kernel has to handle it and sends it to the user process. Now, what I'm working on is an editor inside an SSH session, so okay. Well, the kernel sends it to my user process, which is the SSH client, and the SSH client then wants to send this data to the remote system, because the purpose of the SSH client is for me to behave as if I am logged in on the remote system, even though, of course, I am not, and I'm typing on my own laptop, because I don't know for sure, but I'm guessing that ECE Ubuntu does not have a keyboard connected to it. So that results in this network request which gets sent out, and that obviously involves some interrupts because we're sending the network request. And then the network request is delivered to the remote server, fine, where it generates an interrupt saying, hey, something happened. And then the kernel on the receiving system has to process the event and deliver it to the appropriate process. That happens to be the editor that I have open. So then it appears inside the editor and, well, it takes action. So the editor processes the key press. Let's imagine I'm not doing anything fancy, so I'm just trying to type that letter into the text area. And if that's the case, then great. All we have to do is add it to the text area and update the screen, because the screen shows you what you've currently typed in. It's much harder to type without it, which is why typing your password doesn't always succeed the first time. And when that happens, right, the state of the screen needs to be sent back to my client on my laptop. So that generates a network request and delivers the new state of the screen. And my laptop will take that interrupt and process it and reflect on my screen the new state of the screen. Okay, so that was a lot, right? That's a lot of calls every time I press a key. There's a lot of operating system involvement here. All I did was press one little key. I just wanted some text to appear in a box, and yet, right, we ended up doing quite a lot of work as both the operating system on my laptop and the operating system on the remote server, and that kind of thing is okay. From the point of view of both systems, actually, I type pretty slowly, right? I'm certainly not some sort of award-winning fast typer or anything like that, but even if I were, for the computer, it's pretty slow as far as it's concerned anyway. The problem is, what if it's the day that an assignment is due, right? Imagine there are 300 people using this system right now. Then what? Okay, so how to address that? So in the book there are two approaches that I personally would describe as somewhat questionable. The first one is the idea that the SSHD program, well, the book actually says Telnet, but I don't want to revisit ancient history this time, and run in kernel mode so there are fewer switches. No thanks. I do not wish to allow the remote login system to run in kernel mode. That sounds real dangerous and real stupid. So maybe we don't do that, guys. Boy, I can't even believe they really suggested that. The other thing suggested is having some sort of specialized hardware to handle incoming terminal connections. Some sort of specific purpose CPU that is sort of meant to handle this workload. And I a little bit feel like I'm taking crazy pills here, because this also sounds very weird, right? I mean, it's less insane, but I mean, typically we don't want to buy specialized hardware just because we log into the machine remotely. That doesn't seem sensible. I mean, it's not that you can't. I'm just not sure why you would. But also, I don't ever remember shopping online, for computer parts where I bought, here's the SSH adapter card so that we can, improve the efficiency of your remote login server. Like, I just don't think they exist. But it's not totally insane, because we have looked at like some specialized hardware for common operations. Translation look-aside buffer, for example, was one of them. So, any other ideas? Okay, so there's a couple of ideas that might actually help, right? Something about the translation look-aside buffer was based around the idea of, well, can we take something that would normally be a slow software operation and can we speed it up by doing it in hardware and potentially in parallel? And for some complex devices, including hard drives, it's possible to just push actual work to the device itself, which speeds up the operation and simplifies the system, because it doesn't have to work as hard, because the hardware or firmware of the device is capable of doing the thing that we needed. So that sounds pretty good, all considered. But again, I'm not sure how that necessarily applies for the SSH approach. The other problem, of course, with buying specialized hardware for this is hardware costs money and is not necessarily easy to get your hands on. Trying to get a graphics card during the past couple of years. Okay, next idea, right? What if we sort of wait for a bigger chunk of data? Does that help? I mean, it doesn't help in this specific scenario, because when I press a key, I want to see the key press reflected as soon as possible, particularly because, what if I typed it wrong? I want to know about that sooner rather than later. So that sort of thing, we can't just wait until I've typed a full sentence before we actually start submitting the changes to the remote server, because that would be a little bit weird. Could we use DMA hardware? Make use of DMA hardware to reduce the involvement of the CPU? That one actually might be plausible. That might work. We might be able to successfully deliver the thing to the location in memory much more easily than we would actually having the operating system wake up and deal with the interrupt and do all of these things that we needed to do. So we might be able to eliminate a couple of the steps, and if we can get it down from 6 steps to 4 steps, maybe that's enough so that this operation can be completed efficiently, at least enough that nobody feels really sad or that the system doesn't feel overwhelmed. So it's at least an idea. Okay. And to close out the topic, I want to talk about security in I/O devices. This joke used to be much more obscure, I think, until they went and released a sequel 36 years later or whatever it was to Top Gun. So now probably at least some people get this joke, but you're in the danger zone now. The problem that we face with device drivers is that they run at a high level of trust from the point of view of the system, which means that a vulnerability in one of the device drivers makes it very easy to exploit the system. Now, if a driver allows for privilege escalation, that is to say, taking a non-privileged action and doing it in a privileged capacity when you're not supposed to, that might actually be a really, really big problem. And attackers will look for these things because if it does allow privilege escalation, so you can do things you wouldn't normally be able to do, or you can spy on other operations that you shouldn't normally have access to. Like, yeah, of course attackers are going to want to do this. And it's much easier to use a vulnerable device driver that exists in the system than it is to try to compromise the system in the first place. Right? Because how do you get the malicious code into the system? Well, what if the malicious code is coming from inside the house? What then? Right? So this does presuppose that the vulnerable driver is in fact on the target system to begin with. So how does that happen? Now, okay, like one possibility, of course, is if an administrator wishes, they can intentionally install a vulnerable device driver on the system, and that will allow bad people to do bad things. That's kind of silly though, because if you're an administrator on the system, like you can already do bad things. You don't need to install a device driver to allow yourself to read files that don't belong to you. As an admin, you just change the ownership of the files, and then congratulations, you have access to them, even if you shouldn't. So that isn't really the way. So, okay, what about this? What if instead the device driver that's installed was vulnerable, but we didn't know that at the time, right? Bad device drivers should not get installed because there is device driver signing. But here's the thing, not all problems are foreseeable. Right? Bad drivers being installed are hypothetically prevented by the operating system showing you a lot of warnings saying like, hey, are you sure you want to do this? And ideally you heed the warnings and you choose not to install the vulnerable device driver, and that makes your life better. But of course, do people actually follow those warnings? Do they pay attention, or do they ignore them? The answer may depress you, but yeah, most likely people ignore these kinds of warnings, like yeah, click OK, whatever it takes for me to be able to print. Okay, like please, I just need to print this document. Why won't it let me print? But okay, let's imagine then that people don't necessarily ignore them, but even if people pay attention to the warnings, that's not necessarily a complete solution, because there is the possibility that there is a vulnerability in an otherwise not malicious, so legitimate driver. And such a driver would have been tested, approved, and signed, and the problem is only discovered after the driver is shipped, after it's released, after people have already installed it in their systems. There wasn't any malicious intent. Nobody went out of their way to put a vulnerability into the driver, we're imagining in this scenario. It just so happens that there is one, and it's discovered after the fact. Okay, so why don't we just update? We'll get there. All right, if a fix is prepared and published, that's a big if, because lots of devices are made, and no maintenance is done on their drivers, and if there's a vulnerability, it's too bad, so sad kind of situations. Support the device. No, don't be silly. We don't do that around here. That may or may not be the case, right? Let's imagine also that it's probably not, and so a fix may be created, and then it does have to be shipped, it does have to be installed, and whether people are on top of installing those fixes is a whole different discussion. One would hope, but there's no guarantees. However, the previous version of the driver, vulnerable as it is out there and still has signing. So what do we need to solve that? Yeah, I mean, to solve that, we need a concept of revocation. And revocation is nothing more than being able to revoke the approval of a driver that we now know is vulnerable. And that's not anything that should be super difficult, and yet. and yet. So Microsoft, I don't intend to pick on them too badly here, but Microsoft does in fact have a block list. And the block list is used to identify drivers that previously had been approved, but we now know have a vulnerability in them to effectively prevent them from being installed when we know that there is such a vulnerability. So there is a source that's linked in the notes that discovered that Microsoft had not been properly applying updates to the driver block list, which did actually result in some exploitable drivers being installed. Or as Obi-Wan says, oh, not good. Mild understatement. Mild understatement, yeah, as one does. So Microsoft did address this problem of not updating the block list correctly once it was reported, but there were some known cases of actual exploits taking place using drivers in the block list as a result of the system not correctly updating to cover these situations. That's not nice. Such things are very difficult to prevent in its entirety, but it is a little bit painful that there existed a mechanism for dealing with this, but it didn't work, because that's frustrating, because if it could have been prevented, that would have been so much better, wouldn't it? Anyway, as you may imagine, though, the installation rate for patches to operating system is never 100%, and because of that, right, there is sort of always the possibility that vulnerable drivers do exist out there in the real world. Vulnerable systems, accordingly, will continue to exist, and therefore, we can never be completely safe, even if we do our best to sort of keep on top of all of the security updates and install them in a timely manner. And that's the state of security in input and output devices and their associated drivers. Okay, with that said, in our next topic, we're going to talk about disk scheduling, going back to something that we talked about just recently, around the idea of, well, how do we deal with the fact that there might be non-uniform memory accesses, so or non-uniform resource accesses, and that's what we're going to consider in our next topic.